So let's see here 3 formulations of a problem. I'm interested in the first one, problem P1. That's the, whoops. We're minimizing a cost, which is the sum of the monetary cost plus the max of the penalty. Right? That could be one way of defining the problem. Which of those formulations, if any, is an implementation of P1? So understanding this type of transformation is essential for the practice of what we're doing. We will see problems formulated in this or that other way. Very often we will see A or B, but it's not easy to reason over A or B. A or B are formulations that are for solution. P1 is the formulation for reasoning about what we're doing. So let's see the solution. I close the poll. And I'm not very lucky with answers, but I have a tie between A and B. Let's see. The correct solution is B. Is A, sorry. Whoops. Let's see why. Whoops. Here's the problem. Here I'm rewriting P1. Here is the problem that we were solving. Then I simply rewrite the max here, which is a max of, which is phi is itself a max of 3 things. Is the max of 0, this linear function, and that one, which is given here. It's the max of 3 functions. So we have a max of max. And we know a max of max can be taken as the overall max. To make things very detailed, I call LIS each of those 3 things here. So it's the max over S of the max over I of LIS. So it's like our mice and elephants. We have a function of 2 indices, I and S, but here we take max of max. And we know max of max doesn't cause any problem. It is the same as simply saying I'm doing the max over everything together. If I scan all the values of I and S, and I take the overall max, it's the same. That is step 1. Step 2, we have seen last week the max removal transformation. We have seen that if something is a sum of terms plus a sum of is one term plus a sum of functions that each of them is a max. So here we have one function that's a max, one term plus one function that's a max. Then we know that every max can be replaced by an additional optimization variable that I call here epsilon. Not the same epsilon as the coefficient, the efficiency coefficient. I call it epsilon here, and we know that we need to add the constraint that epsilon is larger than all the constituent members that we were maxing upon. So here, that gives the constraint. Epsilon has to be larger than L of I and of S for every S and for every I, which gives us exactly the constraints on problem A. That means we need that epsilon is larger than each of those 3 terms. That's the over all I part. And it has to be true for over S, which was exactly problem A. Problem A, we're saying epsilon is larger than each of the 3 terms. And that means 1 inequality per term. That's another trick we know. Being larger than a max means being larger than all terms. And that has to be true for all S. So A is the formulation of P1. I stress here it's important when it's very easy to write a problem like this, and you see very often projects or papers that write directly the problem in this form, but it's one step is missing. If you write it in this form, you should be able to reverse engineer and say, this is exactly what I am minimizing if I do this. So if I do this, I'm minimizing a cost function, which is the monetary cost, plus the worst of all the penalties. If you do this, that means you take the penalty very, very strictly. You think that you will pay for over every time, over all the time steps that you have, you will pay for the largest penalty, not for the sum of all the penalties, which you may want to do, but you have to be aware that if you do this, you are extremely conservative. You want by all means to avoid any single penalty. You will pay the worst and not just the sum.
Excuse me?
Yes?
I don't really understand why B is not correct.
Let's see this exactly now. Thank you for your question. Let's see what B is doing. B is in fact equivalent to this one, where we had taken the sum of the maxes, the sum of the penalty functions. Why? Well, we can do, instead of going from B to P, I will do the other way around, from P to B. Because we know the max removal transformation, we know that the max removal transformation is recalled here. If I need to minimize an objective function that is one term, plus a sum of term where every term is itself a max. Then I can replace every max by an optimization variable. So here, that's exactly what I have. I have a sum of sums, so it's the sum of the PS here, plus the sum of all the penalty function. And every penalty function is itself a max. So I can replace every max by one variable, which is what I should do. So if I replace every max by one variable, I will have one epsilon t here, one epsilon t plus h minus 1, with the constraint that epsilon is larger than the penalty. And that gives exactly problem B. Problem B says I have a sum of epsilon s. So for every phi, I have one additional variable, and the epsilon must be larger than phi, which is equivalent to this here. So your question is important. It's exactly the trick. This is why we do this module, and this is why we do those quiz. It's very easy to think that this is correct or that is correct. Why is difficult if you don't do exactly formally the step like we're doing now. So if what we care about is the integral of the penalty functions, which depending on the weight we put, that's essentially saying we care about what in average the penalty is instead of the absolute worst case. This is what we should be doing. So problem B is, in fact, problem B is exactly the practical implementation of our optimization problem. So if this is how I solved it, and I showed you diagrams showing the solution in the first hour. To solve this problem, you can implement exactly problem B. Voilà. In some cases, we will need more generic transformation. The max removal transformation is an instance of a more general transformation that we will see now, which doesn't have a name. So I'm just giving it the name of supplementary variables. So these things we're seeing now, they're usually not given in textbooks. It's just by my experience of analyzing optimization problems written in the context of smart grid that I found that people are repeatedly doing those transformations and sometimes doing them wrong. So here what I put is a generic result, which seems a bit abstract, but we will see examples. So that's the price to pay. If you want to be a bit generic, you have to live with some abstract representation. But I will explain that it's not as complicated as it looks. Assume I have an optimization problem where there are constraints. So here I'm not focusing on the constraints, so I put them through the domain X. So assuming X belongs to X, that captures all the constraints. We've seen that depending on how you want to use duality, it may be good to put some of the constraints in the domain, some others into explicit constraints, but you can always put whatever you want, at least to describe the problem. So here that means there is a problem with constraints, and I'm focusing on the objective function. The objective function, I'm assuming it's a function of the optimization variable x, but I can specialize this function by saying inside the function I can recognize some expressions, which I call f1, f2, fn. That are perhaps embarrassing. Perhaps those are the ones that have the max or other more ugly things, perhaps. So they can be anything. They are just arbitrary expressions of the optimization variable x. When I say variable, it's a vector. It's a variable of any dimension. And I'm making one very important assumption, is that the objective functions is monotonic increasing with respect to each of the expressions. If it's decreasing, it will not be a big deal. I just can, the same theory will apply, but what's important is monotonic here. Monotonic non-decreasing means if I increase the value of the expression, not the value of x, the value of the expression, with respect to the expression, the objective increases when the value of the expression increases. So that's a very weak condition, but still needs to be verified. Then if I have that, I can replace every expression by a supplementary optimization variable. Here I've replaced f1 by epsilon1, and I add the constraint, so there are already constraints in capital X, I keep them, but I need additional constraint that the variable I've added is larger than fi of x. So it's almost obvious. I give a proof in the next slide, but intuitively it's obvious, because if you do it the other way around, if you look at this problem and you say, what am I doing when I'm solving this? If I look at the constraint on epsilon, there is no joint constraint between epsilon and x other than the one that's given here. So if I apply the associativity of mean to compute the overall mean of this, I can first fix everything and take the mean over epsilon1. If I take the mean over epsilon1, I will say, what are the constraints on epsilon? Well, it's anything larger than or equal to f1. Now, if everything is fixed except epsilon1, we know that with respect to epsilon1, h is increasing. That's this hypothesis here. So if I want to minimize, I should have epsilon1 as small as possible, which means it should be equal to f1. So I can say that if I take the mean first with epsilon1, I obtain h of f1 of x. And then I can continue, and at the end I will obtain that the mean, if I eliminate all the epsilon, is obtained as h of f1 of x, f2 of x, fn of x, which is exactly what I want. So it's almost obvious, it's not a big deal, but it's so important, we do it so often that it's worth putting it concretely. For example, let me look at a toy problem that will show that this constraint can be used, in fact, either to add variables or also to remove. Here I'm showing an optimization problem. I want to minimize exponential 2x plus 3y minus this linear combination of x and y. X and y must be non-negative. So that's my optimization problem. Here I've made the constraints explicit here, which means I will need to keep them all over the place. I can apply my theorem in a zillion of different ways. It's up to me. Here I'm applying by saying I consider that this objective function is some terms that depend on the optimization variable, xy, and the first expression. This expression, I call it f1 here. So it means I can replace this expression by an optimization variable. I could call it f1, here I call it epsilon, it's the same. That means if I replace this, I have to minimize epsilon minus 5x minus 7y. So we have now linear objective. But we need to add the constraints that epsilon is larger than the expression that it stands for. We still need to verify that the transformation is correct by applying the result. So we can say that this objective function is a function of a first expression, this minus 5x minus 7y, and f1 is this quantity exponential 2x plus 3y. The question to answer is this increasing with f1? Yes, because it's the sum of f1 plus something else. So if I increase f1, I increase the objective. So the answer is yes, I can apply it. I can do the same where I consider that the expression is not f1, but the argument of the exponential. Then I have exponential f1 minus 5x minus 7y. And here the same question, is this objective function increasing with the argument of the exponential? And the answer is yes, because exponential is increasing. So I can do the replacement. It's the same as that, meaning of exponential epsilon minus 5x minus 7y. And now the constraint is epsilon larger than 2x plus 3y. You see that we have radically different problems. This one is linear in the objective function. This one is linear in the constraints. Both can be first steps towards making it tractable. Or there can be also steps in the other way around. If I see this problem, perhaps I can remove the epsilon to obtain a problem that's simpler. Of course, it works in both directions. Here I'm using a third example where I say I can observe that its expression, this objective function, is the sum of three expressions. There's a minus sign, but minus 5x is the addition of minus x. So I consider it the sum of three expressions, and then the rest does not depend on x and y. So this is void here, where f1 is the exponential, f2 is minus 5x, and f3 is minus 7y. So I can add three optimization variables, and I need to add the constraint epsilon larger than f1, eta larger than f2, which I printed by in this way. This is equivalent to saying eta is larger than minus 5x, and similarly with zeta here. So this problem is exactly the same as that. Those are the kind of transformation we are constantly doing in practice when we use optimization to solve control problems. So let's exercise your understanding of this transformation on this problem P. Here I'm proposing a problem P that has absolute values. This is a nonlinear terms, and I'm proposing three solutions, A, B, C, not solutions, but three equivalent formulation, which, if any, is a correct rewriting of the problem. So that's a bit of a more complex quiz. I close the poll in 5 seconds. And the correct answer is the majority vote, F. Let's see why. Well, let's see first that B is true. So I recall the problem here. Here I have to maximize the max of two expressions. So I can say that I can write this in the form of max plus f1 plus f2 of this. So the embarrassing expressions, I give them a name, f1, f2. And the question is that increasing with respect to f1 alone? So if f1 increase, does this resulting thing increase? Yes, because the term here will increase, and if we take the max of the two, it will increase. If we take the mean, it would still be increasing. So this is increasing with respect to f1, it's increasing with respect to f2, therefore we can apply the transformation, which gives us this expression here. I add one variable for f1, one variable for f2, and I add the constraint. Epsilon1 should be larger than 2 absolute value of x. Epsilon2 should be larger than -3 absolute value of y. C is also similar, except in C, I consider that the expression is everything here. No, sorry, C derives from B after simply applying the max removal transformation. So once I have written B here, I'm saying this is the max of two expressions, I call it eta, then I must have that eta is larger than this and that, which is exactly what we've added here. So B is correct through the new theorem we've seen, and C is also correct deriving from B. A is incorrect, in fact. A would be deriving from an incorrect application of our transformation, where the monotonicity is not true. I could say the objective function is the max of x plus 2f1 minus 3f2. So my first expression is f1 and f2. But the second expression is a problem. If I increase f2, then I decrease the objective function. So it's not white sense increasing. So I should put a plus sign here to make it increasing. So this is incorrect. And this formulation that we have here is incorrect here. In fact, you could see that this transformation makes the problem convex. The others are non-convex. And the transformation we say, they don't change the convexity of the problem. We have seen max removal. In fact, I could have presented first the supplementary variable transformation, because in fact, max removal is just a special case of this. I didn't do it because I prefer to do it in 2 steps, because that's because that would be a bit complicated. But if you think about it, if I have a problem of this form that we have seen in the max removal transformation, minimize f1 plus fn, etc., plus h of x, which is given here, where every f is itself a max of other expressions. Then I can apply the supplementary variables and say, well, I recognize in my objective function something that's the sum of n variables plus something that depends on x. And of course, this is increasing with respect to each of the expressions, f1, etc. So therefore, my original problem, I can replace it by adding one variable per f. I obtain the min over t and x of this, t1 plus etc. tm, subject to the constraint that every supplementary variable is larger than or equal to the functions that it represents. And then we know that being larger than a max is equivalent to being larger than each of the members of the max, which is exactly giving the max removal transformation. So now you can forget the max removal transformation if you master the supplementary variables transformation, because this is just a special case. But it will be useful to cases that are a bit more complicated. For example, here is one we will see in part 3 of the lecture. We will be confronted with a problem of this shape here. So I prefer to analyze this problem now that we're in the technical parts of the lecture. Assume I have to minimize over some variables that are the control and state variables of my problem. I'm minimizing the max, an objective function, which is itself the max over capital I expressions, every expression being itself a sum, but itself contains a max here. So I have a max of sum of max. To get rid of the complexity, we can apply the theorem of supplementary variables and get rid of all those phi expressions here. Because obviously, if I consider the objective function as the max of the sum of the p plus f, then everything is with positive signs here. If one of the f increases, the sum will increase and the max will increase, or stay the same, but it will be monotonically increasing in the white sense. So we can apply the transformation and say that our problem is equivalent to what we obtain when adding an f variable here to the max here, which is now a bit better here. Of course, we need to add the constraint that f is larger than phi, but this is something we'll be able to get rid of because we know that phi is itself a max here. Then we have obtained here a problem which is a maximum of things, so we can apply again the supplementary variables in this special case, which we called already the max removal. So I add one further variable, epsilon, and we obtain that we have to minimize epsilon subject to the original constraints we had in the problem. Epsilon must be larger than each of the members. So for every I, epsilon must be larger than this expression of I. But now for every I, we have a linear expression in the variables, and f should be larger than that. But we know that phi is a max, so this is equivalent to saying that f is satisfying those three inequalities here. So this is how we can transform our problem that was a bit complicated. It had max of some and max. So a simple way is to go through that. Now we see that everything is linear. Here I rewrite it simply more prettily. This will be our final form. I make W appear here, and this will give, this minor cosmetic change will give us the final form of the problem. We see that we have an optimization on the original variables of the problem, plus all those variables that are the price to pay for transforming the problem and making it linear. Voila, so that's the technical part of this, at least the technical part in problem writing. We will be often confronted with max and means and sums. So max of max is overall max, mean of mean is overall mean, order does not matter. But max of mean is usually not the same as mean of max, so you have to be careful. And one way to be careful is to introduce supplementary variables to get rid of all the things that are embarrassing. Voila. So why did we do all this? Well, it is to be able to do a variant of MPC that is often done, which is called scenario-based robust MPC. There are multiple ways to do scenario-based MPC. We'll see one of them. The idea here is, again, as we saw last week, is to capitalize on additional information we may have about the worst case. In the MPC we did so far, we knew of the future only a forecast. That was already very powerful. We saw that that allowed our heating system to take decisions that were anticipating high cost periods, for example. However, there was a risk that the system was doing. It was at every point in time, it was computing a control action that was based on the assumption that the forecast is true. What if there is a large deviation from forecast that could cause some of the constraints to be not satisfied? Perhaps for a heating system, we would not do this, because for a heating system, the constraints are soft, and if we violate them by a small amount, if we repeatedly solve the MPC, then it will be no big deal. But perhaps for other grid control applications, like if you remember, we had a small grid control where voltages could be a problem, then it might be more of a problem if the voltage gets out of bound, for example. So the constraints you may have may be stricter. In that case, it may be important to make sure that the control actions we're implementing will work in the worst case as well, not just in the average case. This leads to scenario-based robust MPC. I will explain it on the example of the heating system. In the lab, you will have to apply it in the context of an OPM. I explain it here in the context of the heating system to keep the description simpler. So assume here we're paranoid about the temperature and we think the world collapses if the temperature becomes too high. So we care about the worst case here. So in that case, we will need not only forecasts of the temperature, but also not only point forecasts, but also what we call prediction intervals of the temperature. So for those are given here. Here the plain black, the dotted black lines are prediction intervals for the temperature. If you look on the forecasts of Météo Suisse, for example, you will see that they give such prediction intervals. So if I know this prediction interval, if I know tomorrow there's an uncertainty of 2 or 3 degrees, it's not the same as if there is an uncertainty of 15 degrees, for example. Some days of the year, it may happen that such a large uncertainty occurs. So assume I have this. I can capture that by saying I have now 2 extreme scenarios, one for the worst case, one for the best case. Would be the best case here, this would be the worst case, and perhaps one for the average case, which is my forecast I used in the previous case. In general, things may be a bit more tricky. Here, it's a simple case where I care only about the worst and the best case. When you do forecasts of wind energy production, for example, there is not a best and a worst case. For what happens about the uncertainty of wind is that when the wind blows is subject to uncertainty about the amplitude of wind. This is captured by best and worst case, like I'm doing here, but also about the time, the offset in time when the wind will blow. Perhaps the wind will start to blow 1 hour later than anticipated. In that case, the scenarios would be a bit more complicated. We would need not just 2 extreme scenarios, but a whole set of scenarios, perhaps 15 or 20 different scenarios, depending on the offset here. The wind will start to blow at the time it is forecast, but perhaps 1 hour before, or 1 hour after, or 2 hours after, for example. And for each of those, also, what is the intensity, best or worst? So the combination of these, for example, if we have 4 possible time offsets, times 2 intensities give us 8 scenarios, plus the average 9 scenarios in total. So this is in general how scenarios would be used. How does scenario-based MPC work? Well, first, as before, we observe the current state. Now we consider each of the scenarios as being a prediction of the disturbance in the future. And for each of the predictions, we will compute a sequence of actions. But we add, and it's the trick of this, we add the constraint that at time t, so we are at time t now, we want to compute the next action, which we call the action at time t. This is the action we will implement. We will not implement a different action for different scenario because we will know which scenario is occurring only after the fact. So we compute a trajectory that's different for every scenario, but except for the very first action that must be the same for all scenarios here. And then, as usual, we compute the cost. And the cost will be typically the max over all scenarios of the cost. So for one scenario, the cost is whatever we had, it's like before, but we will compute the max over all scenarios. And then the rest is as before. We implement the action U. Nature will reveal the disturbance, and then we will repeat that with new future scenarios, and we will continue. If I take the analogy of my driving car application, here I'm showing 2 scenarios. It's like saying, well, I have the dark blue scenario that says this is how the constraints will be, and have the light blue scenario that says this is how the constraint might be in this scenario. For each of this scenario, I compute what I think I will do, which gives me those 2 diverging trajectory. But of course, now, the action I'm doing now must be valid for all those scenarios. So I will take an action here that must be valid for the 2. You see that for the light blue scenario, this action is not the optimal one, and for the dark blue it is not, but it is constrained to be valid for both scenarios. So both scenarios will influence the action I'm taking now. And in my optimization problem, the scenarios diverge after the first action is taken. Of course, nature and noise, unknown things will make sure that the real thing will not follow any of the scenarios, so we'll redo it from that point and continue. This is how scenario-based robust MPC works. If I apply this to the house, then I obtain this problem. I have to minimize the cost over the control action, but the control action implements also some state, so I have to, the simplest way is to take the state also as an optimization variable, an indirect optimization variable, one that I'm not interested in, but that one that results from the initial state. So capital T at time little t is not a variable, it's considered as data is given. But if I choose the action U in scenario I, that gives me a certain trajectory of the temperature. Then I have to choose my actions for every scenario and for every time, but I'm constraining that at time t, the first actions I will take, the actions must be the same. And the cost for every scenario is the monetary cost I will pay plus the penalty, and I take the max over all scenarios. So this is what scenario-based robust MPC will do exactly. So that leads to this optimization problem that we have been able to write in a more pretty form a few minutes ago. So here we need theta hat. So theta hat, the disturbances, they are different for every scenario. So they correspond to the outside temperature for each of the three scenarios I mentioned. So here capital I will be 3. We have seen how to get rid of the ugliness in this optimization problem. So this is in practice what we will solve. But the important thing is to be able to write this, but also to be able to write that. So this is what we can do when we want to reason about the problem. If somebody is asking, am I happy with the way you formulate the problem? Then we should look at this. If somebody wants to solve it, then we have to look at this. Understanding the problem we're solving from this is not so easy. We may need to do a number of transformations, but now you know how to do those transformations. So I applied this for the same scenario, the same data we had before. So this is what we saw an hour ago. This is what the MPC will compute. So the MPC knows only the average, the point forecast, the dotted black line here. Here, this robust MPC knows not only the forecast, but also bounds. So it thinks it will compute actions that whatever happens to the temperature will make sure we will stay within the temperature bounds here. We see what's the price to pay. The price is a bit larger, 5.9 versus 5.8. So we will pay 10 cents more in one day, or at least on this day, we'll pay 10 cents more. And we'll see also where things are different. We'll see that this MPC will start a bit earlier to heat the house because it's ready for the worst case. The worst case scenario would be that the temperature is lower. So if it does exactly this here, it might not be able to reach the best thing here. It would be forced perhaps to do some heating when the prices are expensive. So in order to not do this, it anticipates. Of course, this anticipation here is useless because the temperature, which is the blue dotted line here, blue dashed line here, is not following the worst case. So this is an anticipation that was useless, but it was ready for the worst case, and we pay a price to this. So being robust always has some benefit. You will satisfy the constraints in all cases, but in average, you will pay for that. That's a story we heard already last week. Uncertainty and robustness cause a price here. Still, this is robust in the sense it's more conservative, but this one was also robust. As we discussed, it adapted to the different day. Day 2 being different led to different actions to be taken here. Here I took the same two methods, but with different days here, different data for the days. Here the temperature was a bit lower, so it was closer to the worst case, in fact, at least on the first day. Here we see that the MPC is in fact achieving a lower cost than the robust MPC is achieving a lower cost than the non-robust MPC. And this makes sense because now the true disturbance trajectory is close to the worst case, and this scenario is optimizing for the worst case. So it is cheaper for the worst case. So we will pay a bit less here. Here we will pay a bit more here. So this is how things will be with robust MPC. There's a price to pay in complexity. Both variants of the MPC give linear program, but the standard MPC gives 3H variables, at least for this simple example here. We see that the number of variables is, roughly speaking, multiplied by the number of scenarios, which is a typical price to pay. As soon as you have renewables in particular, you will be forced to use scenarios, and there will be an increase in complexity, which is why also in practice we want to solve problems that are easy to solve, which are linear problems here. If you have a very complicated problem that requires running the computer for 1 hour to solve it, then it's hard to be robust with that. Some techniques exist, but that's another story. Voila, let's check your understanding with this quiz. Here are two formulations. Which ones are valid formulation of an MPC for controlling the heating system? I close the poll now. There's a tie between A and B, but the correct answer is D, none. Scenario A looks very similar, but if you look at the constraints here, you see that we're requiring that the state variable can follow so this is a typo, it must be TS here. It must follow exactly the temperature at every time step. Admittedly, it's hard to understand the quiz if there's a typo here. So here, we're just saying that the temperature over which we're optimizing must be following all the different disturbances, whatever the disturbance here. But this is not possible. If the set of feasible values is empty. You cannot have this equality true for every value of theta. So this is simply a formulation that if you try to implement it, you will very quickly realize that it's unfeasible. The second here is feasible, but here we're doing something wrong. We're imposing theta as an optimization variable. That means we choose theta, we choose the control, we choose theta, T derives from that. But by choosing theta, we're assuming we can control the outside temperature. Controlling the outside temperature is, of course, not something we can do. So if you could control the outside temperature, you would do this. But of course, nobody can really do that, at least easily. So none of them is correct. Similar questions now about those three formulations. Which of those are correct formulation of the last problem we saw, the scenario robust MPC for the house we're trying to control? So here the question is not how a transform problem reflects or does not reflect an original problem. Here it's more which expression, which we're not trying to transform to make it tractable, but which expression represents what we would like to capture. I close the poll in 5 seconds. And the correct answer is A. In fact, A is exactly the problem we saw a few minutes ago. So that's, if there's no typo, that should be verbatim the copy of the problem we had before. So that's one representation of the problem. If we do this, what are we doing? We consider here we're taking the sum of the max. Now we saw that max of mean is not the same as mean of max. It's easy to see also that sum of max is not the same as max of sum. So here we're saying that at every time step, we consider that the cost is the worst case among all scenarios. You can do that, but if you do this, you would be extremely conservative because there will be no scenario that achieves this cost here. Some scenario might be worse at some point, some might be at another point. So in general, you're too conservative when applying this. So that's a valid transformation of one problem, but if you do this, you have to realize that you're imposing a penalty that is the max over all scenarios, which is not in the spirit of scenario-based optimization. Here, there's a more subtle problem. Here, the problem is that the control variables don't depend on the scenario. So here, we're choosing a set of controls that's feasible. I mean, you can write an optimization problem in this way, but we say we are forcing the optimizer to choose the same trajectory of controls for all scenarios. Again, this is unnecessary conservative. That means now I'm looking at the entire horizon and I need now to choose for all the decisions I will take. But since we're using MPC, MPC means receding horizon, also means we will have the horizon move at every time step. So since we're using MPC, we will do it again. Since we will do it again, there's no point deciding now what there will be. I will have a better decision taken when I have more information in the future. So this is a formulation that is mathematically correct, but does not correspond to what we would like to do when we do scenario-based robust MPC. Voila. The good news is that's the end of the lecture for today. It's a bit shorter, but the lab will be a bit more complicated because we now start to put together all the different elements we've seen. MPC, I repeat, is based on optimization, but it's a control method that uses a receding horizon. The horizon H is receding. Receding means it keeps moving on. At time t, I optimize everything until time t plus h, and at time t plus 1, I will consider a horizon that goes until t plus h plus 1. That's the key trick. That's very powerful. It's used everywhere in engineering and, of course, in grid control. It applies to controlling set points of an energy system, in particular, if there is any kind of storage. Here, the house, we don't usually think it of a storage system, but that's exactly what is happening. The house is storing heat inside its inertia, and this is exactly what the control system was doing in order to avoid having to pay a large amount of money at the peak time. We heated the house a bit more, which is a form of storage. Of course, you can have electrical storage. In the lab, we'll see that. Well, a battery, for example, which is more directly visible as storage and is also more flexible in the sense that in a house you can put in, but you cannot remove the heat from the house. But from a battery, you can, it works both ways. With an MPC, we obtain a policy, although it's not usually formulated in this way. But if you think about it, what the MPC says to you is, given what I have observed at time t, I observe the state, x of t, I take a decision, which is u of t. If you look at the MPC as a black box, it is what it is doing. Of course, in order to do that, it does a projection into the future, but that's the internal mechanics of the MPC, so we can view it as a way to define a policy. Compared to the other policies, it's nonlinear. In fact, we don't know exactly how the policy is. It's very complicated to understand and analyze what an MPC is doing and why. So an MPC might provide results that are very different from linear policies that we saw last week. It's more complicated also, so both forms of controls are very widespread and you need to master both of them. Compared to the other controls, MPC has this property of looking ahead, which is a benefit, but also a price to pay. We will need to do an optimization problem, which is much bigger in space because we look at a number of time steps multiplied by scenario if we do scenarios. And we will need forecasts also. So it's more complicated, but usually works better when forecasting and when looking ahead is important. We have seen a number of manipulations of mean and max, and through the quiz, how it's also easy to get confused. So now with the generic methods we have seen, we should have systematic ways to transform something into a problem that becomes linear. In particular, it's important to have this step of formalizing your problem without worrying about how you will solve it, and only then get rid of the mean and the max and things like that. And we have seen that an MPC is very robust. If you need to make it more robust, in particular to make sure it works whatever the worst case could be, then the best used known technique today is that of scenario-based robust MPC, as we have discussed.